This is the Earth Science Classroom. Welcome back to the channel. This video is on metamorphic rocks, and in particular we're looking at the types of metamorphic rocks and giving you a little bit of a brief overview of each type, what's going to happen in each type, and the kind of area and location where these exist. And we're going to look at bringing you into the correlations and connections between these types. Okay, so we have the types of metamorphism. So again, metamorphism is the process of change and the form whilst in a solid state. So this is basically an isochemical reaction, and this is before we get to melting. So before we get to melting, so we have higher temperature and higher pressure in certain conditions. And there are two main types. Okay, so the two main types would be local, and the other one would be more regional. Now, obviously, by the terms, regional would be large scale, a large geographic area, and would encompass obviously a large area, but also time as well. Now, local would infer that it is a smaller amount or area that is being changed, and also we can have a lot more differences over an area based on the different types of local metamorphism. So let's start with the first one. All right, so the first one obviously is one of the main types, regional, and this is to do with large-scale tectonics. All right, so I have my little subduction right here and the break off. This is my mountain. This is my orogeny. This is my fold mountain. This is my Himalayas. This is my Aravalli fold mountains in India. The Appalachians that are very old. One of the oldest mountain ranges in the world. The Urals are actually the oldest, but the Appalachians are pretty old, at around 480 million years ago, and sections of the Appalachians is going to be a fold mountain situation. So we have these beautiful mountain ranges that are caused by tectonics, and they are large areas. Obviously, the Himalayas is a very large orogeny belt, so we can put orogeny or orogenic belts. We can put fold mountains as well as an example, and we have obviously the convergent plate boundary with continent smashing into continent. Case of the Himalayas, it was India and Asia. So what we're looking at is a very common type where we get different grades and different levels of metamorphism based on the temperature and pressure and the conditions, and also the depth. So what we do get is what's called index minerals, which is certain minerals that form only at certain pressures and temperatures. So this is like the Bowen's reaction series, where at certain temperatures these minerals are going to crystallize. It's the same thing with metamorphism. At certain pressures and temperatures, based on certain depths, in these conditions you will get a certain mineral because of the stability of that mineral and the elements and chemistry. The stability will make certain minerals certain conditions, and we call these isogrades. Okay, the isogrades are going to be the boundary between each definitive mineral type that's formed at a certain temperature and pressure. So you can also look at the Saussure line, and this is a collision zone as well. And with that index mineral, you can say that in certain areas of that orogeny belt, based on the depth and the pressures that are introduced to that protolith rock to change it into the metamorphized rock, the end product, you're going to have different grades, and the grades go from low to intermediate to high, and you can get all these different types with regional metamorphism. Now, regional is probably the most common, and by the amount is again the most common. However, the next one is contact or thermal metamorphism. So this is also common, and this is an example of a local or small size, small area metamorphism. So what happens is you have the rock that is, say I have my rock right here, okay? And I have intrusion, some magmatic intrusion. Basically means the magma has been put into this rock, okay? So I'm going to put magma, and I get my little magma. There we go. Okay, so the magma is between 850 degrees Celsius to 1500, let's say, is a nice range in Celsius. Now, this temperature, it's going to burn. It's going to burn any rock that is around the magma. So it's going to burn any area, any rock that was originally there, this perlith, this parent rock, all right, and it's going to melt and partially melt and burn any contact with this magma. Now, this is called an aureole, or aureole, right here, and what's going to happen is you're going to have increased metamorphism around the magma, and as you go away from the magma into this what's called the country rock, that's the original rock that's surrounding the magma that has been intruded or just put in either from a diapar or a uprising through divergence or some sort of decompression melting, but you get this magma intruding, and the level, so you get different types of metamorphism from higher grade to lower grade based on temperature around this aureole in the country rock. And it's an awesome thing to find in either volcanic regions or volcanic arcs or any kind of subduction zones. Now, next one will be burial. Now, based on this being a stage of sedimentary rock formation, or what's called diagenesis, which is the process of lithification, you would say that this is a local or small size metamorphism. Now, this really is an initial stage for metamorphism. It kind of works on low temperature and low pressure conditions, and it obviously would increase in pressure and temperature based on the level of overburden, and that would correspond to the depth, any kind of tectonics that is working on that area, and also the density and composition of the overlying rock. So this would be part of that initial stage of metamorphism. So burial will be that kind of an introduction to metamorphism. So the next type is called dynamic. Now this again is a local type of metamorphism, and it's to do with any kind of active fault lines. So we can even do the San Andreas fault line system. We can even look at certain areas that are even not active, that were previously active or historically active. So what happens is around the movement you get friction, all right, in these seismic areas, and you get the elastic rebound theory linked to this with deformation, and you get this very thin area right around the fault lines. So let's just draw a quick fault line. So this right here in the middle will be our fault line, and a fault, you have to have movement either way. All right, so it could be a normal fault, it could be a strike slip, which is the San Andreas fault line, and around, basically exactly around in this little zone right here, similar to the aureole with the contact metamorphism, you get the friction and the heat and temperature and pressure of the two sides pushing against each other, pushing in opposite directions. You'll get metamorphism or metamorphic rock being formed. Now, hydrothermal can be linked to contact. So we had the magma diapar or magma intrusion. You might also get faults or cracks or joints, which again can be linked to dynamic as well. Again, this is a local type that you'll get the addition or interaction of water and other dissolved ions and such moving into that kind of country rock and interacting with magma to form different elements, so to chemically change or add, and the metamorphic process would actually increase when you actually have what's called these hydrous minerals. So when you add in the water into these minerals, you're going to get an increased rate of metamorphism. This can happen in mid-ocean ridges, and maybe in some areas where you have local and very shallow depths where you have access to water, say of an ocean plate or a lake. That could also be a good example. Another type would be subduction. Again, this could be local, all right, or depends on the size. You can argue that it also could be regional if you're looking at large-scale subduction, like around the Pacific Ring of Fire. But the increase in depth quickly would increase the pressure, but it would actually keep the temperature kind of low, so between 4 to 14 degrees per kilometer as a lower geothermal gradient, which means that the temperature wouldn't increase that fast compared to depth. The regular geothermal gradient would be about 30 degrees centigrade per kilometer, so this would be a lot slower. So the pressure is the main catalyst in this type of metamorphism, whereby the rock will go through various stages based on depth and pressure, going through between like green schist to blue schist, and then finally into eclogite as a final metamorphic face or facies. And you can actually track that as the subduction, as the slab descends deeper and deeper, and it will react with either water in a shallow depth, or in terms of burial, or even in terms of the contact with magma as well. This is the Earth Science Classroom. Thank you for watching. I hope you enjoyed the content. Check out more videos on our channel, and don't forget to subscribe. Thank you again.